Continue with supervised learning and go a little bit more into depth about how do you actually solve all these things. How do you solve the optimization problems corresponding to the different classifiers. Where should I stand?
There is area.
So I just wanted to put up this, maybe you've seen it already, but this is kind of the typical machine learning thing, right? There's a big pile of stuff. You throw your data in, and if it doesn't look quite right, you choose a different model or you choose a different classifier, and so that's kind of what we've seen. Alright, so the overview for today, I'll try to make the transition from learning to optimization, then basically forget anything about learning and only focus on the optimization. But we keep in the back of our mind that whatever we are doing did come from some applied problem. And we want to also do something with the solution. Then give you a very brief introduction to optimization, basically to introduce you to some terminology that you would encounter when you're reading on optimization. So this should get you familiar with all the lingo that they use and to give you this kind of an idea of what all these terms mean. And in the end, it's not super complicated. So I think we should be able to do that, and then talk a little bit about some current trends that are currently going on, like stochastic optimization and those kind of things that are very, very hot, and that we can actually understand once we've learned a little bit about the basics of optimization. So supervised learning for me, as we've also seen before the break, is basically given features X and data Y. I'm very, very happy that we have the same notation there. So features X and data Y, find a function f such that it approximately predicts well your training set. Right? So once you find this function, then you can go on to evaluate it and to do predictions with it. So for me, it's only right now about finding this function. So we've seen many examples, so I'll just flip through these rather quickly, right? So one of these is like fit a line through these points, but of course there are many lines that we can think of fitting through these points. But again, the question now is, given that I've decided which kind of line I want to fit, how do I find this line? How do I fit it to the data? There's the example from last lecture. If you remember the papayas, you go to the market, you buy these papayas, some are good and some are not so good. So now you want to classify, separate these by drawing lines. So that's also what we've seen. Again, there's many different lines that you can draw to separate these. And again, the way we can think about this is finding a function, let's say, that's positive if the papaya is yummy, and the function should be negative if the papaya is not yummy, and then the lines are just the zero level sets of this function. So it's wherever the function is zero, that separates my space. And again, the question is, once I've decided what kind of line I want, straight lines or wiggly lines, how do I find this function? So that's basically the whole supervised learning zoo that gets you all these different methods. So I'll just go through a couple of these. We've seen two of these before, and show you what the function looks like that corresponds to these kind of classifiers. Once we know what kind of functions we are looking for in these classifiers, then we can think of how to parameterize this function, and then we can think of how to find the parameters in that function. Alright, so linear regression, of course, we've all seen that. So there we typically have a function, and I'm kind of missing the fact that I can't point here, but I'll just try to use my finger. So linear regression, we have a function that's just some w0 plus linear terms in all the variables x. So now we have these parameters w that parameterize the function. Can you see it there? Otherwise there's there. Okay. So now we can use the parameters w to uniquely define this function, and then we want to find the parameters w by solving a least squares problem like this. Oh, does this? It doesn't. I guess it doesn't. No. It's the screen. It doesn't reflect. It's a problem. I can shine, but it doesn't give me anything back. So the parameter is just found by solving a least squares problem in this case. Neural networks. We can write down basically what the functions are corresponding to a neural network. So maybe we are used to thinking of a neural network as this kind of graph structure where stuff moves from one layer to the other and then stuff happens in between. But we can also think of it like this. So I'll spend a little bit of time here to explain the notation. So a neural network we can think of as a function. I put in x, then at first there's some function f1 acting on it, and then the function f1 typically does, let's say just the matrix multiplied by my input vector. Maybe it adds some things, and then it does some, activation function on it. The activation function typically is something linear, like if it's too big, then set it to 1. If it's too small, set it to -1, and anything in between, just set, to anything in between. Then once I'm done, the output of the first function is passed on to the next function where something similar happens, but with different w and b's, and then also all the way on to the last layer. Right? So every fk here is one of the layers in the network. So that's
it's a multiplication between the functions.
These are functions acting on each other.
Acting
that's a good question. Yes, yes. So these are composed functions. So this is f2 acting on f1 of x, f3 acting on f2 of f1 of x, etc., etc. Yes, that's an excellent question. And then the network architecture, right? The connectedness of the layers is determined by the structure of these matrices W. And then the optimal weight, so the entries in the matrices and the entries in the vectors are again found by what we call training, but in fact is solving an optimization problem that would fit the output of my function to the training data. Okay. If there's any questions in between, please feel free to interrupt me. Alright. So support vector machines we've seen, and we can also write down what the functions look like there. And here they have a form typically like this, so there's weights W, and then there's this K, which is the kernel that we've also heard about in the previous lecture. So the kernel you choose, and the kernel then specifies what kind of form your function has. Right, so for these support vector classifiers, so just the straight lines, then the kernel would be just a linear kernel, otherwise it would be something else. And here there's the training sample. So given these kernels, we can set up an optimization problem that looks kind of like this. So there's one quadratic term with the kernel matrix, which comes about by just evaluating the kernel function at xi and xj, two different samples, plus something that measures the difference between my training and my prediction. So I'll come back to this form a little bit later. So again, that's just an optimization problem. Alright. So now we are at the point where whatever classifier I want to do, I can translate it into a certain form of the function that is parameterized by some weights W. And then I can set up a big optimization problem to find these weights. And typically it looks like this. So there is a sum that sums over all the samples that I have to train. There is a loss that basically measures how well I fit my current training point. So the loss should measure the difference between the actual label or the actual data point yi and the predicted one given by f. So slightly change the notation here to make clear that this f depends on w for the purposes of optimization. So an fi means here, so I'll just write it on the board so that we have it at the ready. So this fi of w basically means that this is f at xi given parameters w. Okay, so that's the shorthand notation. So that measures the difference. And then r is something in addition that penalizes unwanted coefficients w. So it's to put some extra regularization, let's say, on these coefficients. And typically you do this to prevent overfitting. So if you have too much freedom, as we've heard before, it's very easy to get this loss to be completely zero on the training data. That's not very, very hard, but typically you don't want it to be zero on all the training data because then you overfit. So then this other term is supposed to balance this a little bit. Then how to choose the balance, we'll talk about it in a couple of slides. You have a question?
Yeah, thanks. And talking about regularization, if you were to use the L1 norm or the L2 norm, how will it impact? Are you too detailed right now?
I'll talk about how to solve the optimization problem with those kind of norms, but I have no idea, in particular application, how that affects the classifier. It's a good question and I can't answer that. Yeah. So that's the optimization problems we're going to solve. The overall structure. Yeah, so this is the last thing I want to say about the slide. So there's three things to remember. It's a sum over many different samples. and there's two terms, one is the loss and the other is the regularizer. Okay? That's the kind of structure that we have. So then if we go back to linear regression, then this is the kind of thing we get. So there our FIs have this form that we've seen before. The loss could be, for example, just the square loss, and the regularizer, let's say it's just the 2 norm on the coefficients W. I don't want these coefficients, I want them to be small. Then in this case, the total cost function looks like this. You can write it as just the squared norm of some matrix X that contains all my training samples and a bunch of 1s. There's the coefficients W, there's the vector of labels that I'm given, and there's the regularization term. Of course, we know how to solve this. You've probably seen that before. In this case, this is just a linear least squares problem, and it has a closed form solution that looks like that. So this is just to kind of connect that this is not something very exotic. It's something you have seen before and probably have computed and have played with. But unfortunately, or maybe fortunately for researchers like me, often the problem does not have a closed form solution, so we can't just write it down and then compute it. It may not have a unique minimizer at all. There may be multiple W's that minimize this thing. Then we don't know which one to pick. It may have too many variables for sampling-based methods, right? So if let's say W was only 2 unknowns, I could just plot the function. I could just make a nice graph of what it looks like as a function of 2 variables and then say there is the minimizer. But typically there's too many variables, right? It could be hundreds or thousands of variables. If you have these very deep neural networks, many variables, you can't do anything reasonable with sampling.
Good, but you summarized it by saying it's a non-linear problem. If it would be a linear problem, you would have a unique solution.
Well, we'll talk about that. But I can also think of linear problems that don't have a unique solution. But yeah. So if I say 2 times x is equal to 2 times x plus 3 times y is equal to 5, then it's a perfectly linear system, but it has infinitely many solutions because I have 2 unknowns and 1 equation. Yeah. It's not as bad in that case, right? It's a very benign non-uniqueness, but still. Yes, but we'll come to the interplay between non-linearity and non-convexity. That turns out to be a more crucial difference. But the upside is that this does have a very special structure that I've mentioned. It's the sum of many things, and then there's these 2 terms, the loss and the regularizer. The other thing we have to keep in mind when we're designing algorithms to solve these kind of things is that evaluation of this cost function may be very expensive computationally. If we have millions of training samples and for each of these we have to forward propagate our neural network and then compute a residual, and etc. Actually computing this thing, evaluating this cost for one given set of W parameters could be expensive. And I'll come to this in a second. If we want to do optimization by, say, basically steepest descent. Who hasn't seen steepest descent methods before? Okay, that's good. So I can just say steepest descent. Nice. So if we want to compute the gradient to do steepest descent, it may be difficult, right? We've seen how complicated these functions are. You have to, basically dive into, let's say, the code of these neural networks and do automatic differentiation or do everything by hand or do. So it may be difficult, and in some cases it may be so difficult that we don't get the exact gradient, but we get something that's almost the gradient. Hopefully not too far away from the gradient. And the other thing is that it's often not clear what a good initial guess for these parameters is. If we could somehow come up with a very good initial guess of parameters W, so that we almost minimize this, then it would probably be easy to improve upon that. But it's often not easy to come up with a reasonable set of initial parameters. So these things we need to keep in mind. Alright, so optimization. Talk a little bit about more into the structure of the cost function. What kind of different losses, different regularization terms can we expect? What are their properties that matter for the purpose of optimization? Talk a little bit about optimality conditions, because we also need to agree on what is a minimum. When are we satisfied? When can we stop the algorithm? Right? And then show you very basic gradient descent method, basically, and some variance, and see how we can basically view as all of these in the same context. Alright, so loss functions, just to give you a flavor of the different possibilities. Why you would choose one or the other, you shouldn't ask me. You can ask him, he knows more about that. But this is just to give you a flavor of what's out there. So a very typical loss function is the L2. So here in this picture you have to imagine that the true label y is here, and then this measures the distance between the prediction and the true label just in a quadratic fashion. You could do an L1 loss function that looks like that. So again, here is the true label, and then it measures just absolute value. If you're really fancy and you want to be less sensitive to very large residuals, you could do something like a Cauchy distance that kind of tapers off if you go out. So then the further away you are from the true label, the less it really matters, right? At one point you're so far away, you're like, okay, I'm really far away. It doesn't really matter if I'm a little bit further. Right? So that's of course with the square, it exaggerates this. It's like, wow, you're far away, now you're a little bit farther away, and it's even worse. So this is typically used if you want to be robust to very erratic data points. So some data point, something went wrong. Somebody labeled a cat as a dog by accident, and this one misclassified label here has a lot of influence on your classifying here only a little. That's kind of weird.
Wouldn't using conjugate gradient then be useful in that particular case rather than steepest descent?
Definitely, yes. We'll talk about the trade-offs between the different methods. Okay. But yes, so depending on what kind of loss you have, it does influence what kind of optimization method you'd like to use. Yes. And then there's these that are insensitive, and they're kind of one-sided losses. So you only want to know if the residual is positive, then it's bad, but if the residual is negative, then it's fine. So these are used for more of these classification kind of things. And again, there you can be something smooth, or it can be something not so smooth, or it can be something that's very fancy. And again, this tapers off, so it's not sensitive to very, very large residuals. Alright. So now, looking at these pictures, you already see some differences, right? This is smooth. This is also, this is not smooth, but at least it's still convex. So come back to that later. This is smooth, but it's not convex. So we see basically the different kind of things that we can have. Regularizers, so things I can demand from my parameters. I can, for example, demand that my parameters are between upper and lower bounds. So it's one of the terms that we saw in the one equation that I was going to explain. We saw some constraints, right? Something needs to be bigger than something else. So that's typical. Regularizers have these kind of forms. So they go up to infinity in places where you're not allowed to go, and they're 0 in places where you are allowed to go. So then the coefficients that you would get that are permitted by this kind of regularizer are, for example, here. So these are just a bunch of samples, and all the coefficients here are between these bounds. A quadratic regularizer, it doesn't really care, it just wants things to be small. It doesn't have to be 0, just need them to be small. And then typical samples look like this. So here's 0, and then they're kind of distributed around 0. Yes?
So the horizontal axis of the
I should have turned them, you're right.
Okay, yeah.
So just in your mind rotate these, yeah. And multiply them by I. If you want, you can also think of this as being drawn from a normal distribution. Okay, that kind of corresponds to the L2 method. If you do an L1 on the regularizer, there's less penalty and larger coefficients, so then also the spread is a little bit larger in the coefficients. And that's like a, exponential distribution. Alright, so that again, in typical regularizers we see things that are smooth, we see things that are not smooth but convex, and we see things that are, convex but they're not continuous. They're going to jump up to infinity right here. Good. Yes, so I kind of mentioned these different properties. I think I can slow down a little bit now. We're on track. So we talked a little bit about the defining properties, so convexity, continuity, and smoothness. So I just wanted to throw some of the lingo at you that is typically found in literature and give you some pictures that, make very clear what these things mean. And maybe you've seen them, but maybe you've not seen the pictures, or maybe you've seen the pictures but not the terms, or maybe both. As you like. Well, something for everybody. So the first thing that comes up a lot is continuity of these functions, so loss of regularizers. And a nice way to think of continuity is the notion of Lipschitz continuity. So then the definition is this one. So function is Lipschitz continuous, which is Lipschitz constant rho if for all these w and w prime we have this inequality. So you need to find one constant, rho, finite constant, for such that this inequality holds for all w and w prime. So if you would think of that as in terms of just a univariate function, then basically it means that my function at every point I can draw this cross here, and the whole function on both sides should lie in between these lines. So the function should be in this fan that's defined here and in this fan here. So none of the functions should be here. Right, and then the larger the constant, the steeper these lines are. So this kind of, tells you something about how fast the function is allowed to grow or decay. So then convexity, probably if you've seen these pictures. So function is convex if this holds, but in a picture, it's basically saying if I have 2 points on the graph of the function, and I draw this line between these 2 points on the graph, then any point on this line should be above the graph. And then the function is convex. And this turns out to be very, very crucial in many of the optimization algorithms if you want to prove stuff. Right? If you want to apply the algorithm, it doesn't matter, right? You can just apply it, see what happens. And usually it does very well. But if you actually want to prove that it does something that it does something, typically this is an assumption that comes up a lot. So you shouldn't be intimidated by it, but you just apply your algorithm. Just keep in mind that it's not guaranteed to converge, right? But in practice, often it does very well. You got a question?
No, I think you answered it because I think I wanted to understand what you meant by proving, but I think you meant that you can find a global minimum or maximum. Is that what you mean?
Yes, we'll get to that also, but I basically mean if I have an optimization algorithm and I want to prove that this algorithm will be guaranteed to converge to a local minimum, or in that case a minimum at all. If I want to prove this, that it will converge at a certain speed, then I need these kind of assumptions. Yeah. So smoothness slides a little bit longer, but it's basically, can I compute derivatives of the function? That's all there's to it, of course. You know that. But there's a couple of things I did want to mention. The first one is that the Lipschitz constant of the function itself, that we saw, this rho, and if the function is differentiable, then I can just look at the largest magnitude of the gradient of the function, and that gives me the Lipschitz constant of the function. So in that case, the Lipschitz constant of the function really does tell you something about the largest rate of change of the function. It's very useful. Then the other thing that comes up even more is the Lipschitz constant of the gradient of the function. So that turns out to be a very crucial property, but knowing what the Lipschitz constant of the function itself looks like, kind of what it does, you can kind of imagine what the Lipschitz constant of the gradient looks like, right? It's basically how fast is the gradient allowed to change. And I'm going to call that little l. So keep that in mind, little l. So in literature it's often a big L, but big L for me was the loss, so hence little l is the Lipschitz constant of the gradient. The other thing that we can, was there a question?
It's simply the second derivative.
Yes, yeah, well, if it exists, yes.
Oh.
I wasn't there yet. Yeah. So this is if there's one derivative, but you're right, indeed it's a second derivative. The other thing that I can, useful property I can look at once I have a first derivative of my function is if it's strongly convex or not. So we saw convexity, but you can strengthen this notion to strong convexity. And that comes with a constant little mu, it's also important, so little mu. Basically saying I can find a quadratic model of my function that's always a lower bound. I'll show you a picture later, it's much clearer. But basically, can I find a quadratic function at any point with constant mu that's always a lower bound? That's the mu. And then the constant L divided by mu turns out to be a very, very interesting property of the function. We call it the condition number of the function. And we'll see in a minute why we call that the condition number of the function, but it basically tells you something about the smallest curvature in any direction and the largest curvature in any direction. And then the ratio between these two, that kind of determines how hard it is to solve this optimization problem, it will turn out.
So now you talk in terms of a multi-dimensional space.
Yes, definitely.
Okay.
Yeah. This is all. These are all functions from Rn to R.
Okay.
Yeah. But it's easier again to draw pictures in one dimension.
Sure.
That's still a shortcoming after all these years. But I had last couple of slides. I have something nice about that as well. Okay. So then Lipschitz constant of the gradient, as was noted, is the largest eigenvalue of the Hessian. But then this should be everywhere, right? The Hessian, the second derivative, will depend on where I am in space. So then the largest eigenvalue would be like, over all points in space, the largest eigenvalue I can find. Then other things I can read off of the Hessian is if it's positive semi-definite, so all the eigenvalues are non-negative, then the function is convex, right? The second derivative is positive, then obviously the function is convex. If the Hessian is positive definite, so it's not zero, it's really positive, then the function is strongly convex, with constant mu being the smallest eigenvalue of the Hessian. But then again, this is the smallest one over everywhere in space. So that's why this L over mu is called the condition number of C, because we can think of it as the condition number of the Hessian. Alright, good. So important thing to remember for now is the L and the mu. So the largest and the smallest curvature in any direction. Okay?
It's just the condition number of the matrix then?
Exactly. The Hessian, it gives you a matrix, yeah. But of course this matrix depends on for which W I put in.
Sure.
And then this is the smallest and the largest one. Yes, exactly right. And there's the picture. So a function strongly convex at any point, for example this one, I can find these two quadratic functions that are upper and lower bounds. And again you have to imagine this in multiple dimensions. Then this one needs to be so small that it's also undercutting the smallest, the slowest growing dimension, and this one needs to grow so fast that it's keeping up with the largest, the fastest growing direction. Okay. To note that these bounds, these L and these mu, are nice in theory, but in practice you can hardly ever compute them. So that's just to keep in mind. We can try to find them out as I'm optimizing the function, but in practice I can't compute these. But it's good to know that at least they're finite, right? You need to know maybe something. But these are used a lot in theory, and in practice, you can't compute that. And then the other really important thing to note is that if you read a paper and it starts with, let f be a strongly convex function, and then you would be, tempted to just put it away, because you're like, well, my function is not convex, so never mind, I'm not going to read the paper. But please do, give it a chance, because these are usually technical assumptions that are needed to prove anything at all. And your function, it may not be globally convex or strongly convex, but typically it will be locally convex or strongly convex, so that whatever results are listed in the paper may still be useful once you start getting close to a minimizer. Okay, so bear with those papers. Papers could maybe do a little bit better way of selling their thing, but just so you know. So then we need to talk about minima. What is a minimum? You know this. I'm going to just skip ahead because you know what a minimum is, right? There's global minima, there's local minima. The global minimum may not be unique. That's the point. So optimality conditions, of course, if the gradient is zero, then it's a stationary point. But it could also be a maximum. I need to look at the Hessian. If that is positive, then I'm at the minimum. For a convex function, I'm just going to leave that for now. You can forget about this. Okay, so then we're at algorithms. So the basic flavor to solve these optimization problems comes in this form, and they're almost all in this form. I have a current iterate, WK. At this current iterate I need to compute a search direction, so a direction in which to go to make things better. and I need to have a step size that tells me how far to go in this direction. Step size needs to be large, so I want to make things, as good as possible, but not too large, so that I make it worse again. How do I compute the search direction? There's many choices. Here's only 4, but there's probably hundreds. One of them is just the simple steepest descent, where I take the search direction to be the gradient. Right? Sometimes it would put a plus here and a minus here, but I chose to do like this. Okay. So search direction just the gradient. If you do conjugate gradients, then it's just the gradient plus some term times the previous search direction, so you keep some memory around. There's weighted gradients, and sometimes, depending on how you make this weight matrix, so you scale the gradient in different directions in different manners. They're called quasi-Newton methods, and then you estimate this matrix somehow. And then there's a Newton method, which you've probably seen at least in one variable, Newton's method. There I take into account the second derivative of the function as well. So if I know something about the curvature, then I can do better, right? Think of a quadratic function, then all the information is basically in the Hessian. If I take one step, I'm at the minimum. So these are different flavors of optimization algorithms. Of course, whatever, we can think of our own things. We just need to keep in mind that this decay, the search direction, goes roughly in the direction of the negative gradient. So what do we know about steepest descent? So this is important to list. What do we know about steepest descent? So this very basic algorithm that you may or may not use. We know that the iterates converge to a stationary point, so a point where the gradient is 0, from any initial point. Right? I mean, of course the objective needs to be continuous here and stuff, but for any initial point, at least I go to a stationary point. So it can be non-linear, it can be horrible, but it does go to a stationary point. Of course I need a suitable choice of the step sizes, but it turns out there are ways to compute this effectively. So you can make a gradient descent algorithm that will converge no matter where you start to a stationary point. But the stationary point doesn't have to be a minimum, of course. So that's what we need to keep in mind. Now, if I have a convex function with a Lipschitz continuous gradient, so now that's a lot more structure I'm demanding from my algorithm, from my function, then the iterates of this steepest descent will converge to a minimum, global minimum in that case, but it may not be unique, at a sublinear rate. So what do we mean by that? We basically mean that for the iterates, if we look at the cost function at our current iterate wk and at the optimal point, or a minimizer, let's say, w star, then I can upper bound this by some constant that I call a for now times 1 over k. So the larger k gets, the smaller the difference gets between the iterate and the optimal point. If I have a strongly convex function, I can say more. I can prove that the iterates converge to a minimum at a linear rate. So there I can do the same thing as here, except replace the 1 over k by a rho to the power k. So it goes much, much faster, and rho smaller than 1, of course. And here, the alpha, this should be alpha k, the alpha should be between 0 and 2 divided by L, where L was this Lipschitz constant of the gradient. Again, I don't know L, so then I need to find a way to compute alpha small enough, but there are ways to do that. Okay, so that's what I know about the steepest descent. I'll skip the complexity. I'll just show you a picture to give you a very rough caricature of what these methods do in practice. So here's a quadratic function. Here are the contour lines of it. It's in 2 variables. And if I do steepest descent, then it typically follows something like the blue path. So notice here, right, that the curvature in this direction and this direction are very different. So that's this condition number here is very high. There's a large difference between the curvature in this direction where the function is very flat and this direction where it's very steep. And then steepest descent will basically start wiggling around and taking a very, very long time to reach the minimum. So that's the order 1 over k that you see kicking in there. Sorry, no, that's not true. It's just that the rho is very small here. should be, it's the row that's very small. If I do something like conjugate gradients or anything a little bit more fancy, I can bypass this, and then here you see in the green line, hopefully, there's no colorblind people that can, I'll just trace it out there, and then in one step it goes all the way there. So here it's somehow figured out that, okay, now I'm at the minimum in this direction, all I need to do is just go in that direction, and I know exactly how far to go. And then of course if you do a Newton method, this is quadratic, it just goes in one step. In terms of robustness of these algorithms, there's also a sliding scale, so steepest descent will converge from any initial point to at least a stationary point. Conjugate gradient and quasi-Newton things are a little bit more finicky. You need to know, you kind of baby them around a little bit to make sure nothing goes wrong. But in practice, if you do everything right, you can get super linear convergence. So faster than this one, but slower than in Newton's methods. If you do everything just right and you're really close to a minimizer, you can get quadratic convergence. So it means even faster. But then you need to be very close to a minimizer. You need to compute the Hessian, all these things. I'm going to leave that. That's basically saying what it just said. Okay, so I think what I'll do, so there's some generalization and things you can do for non-smooth things. So like the L1 regularizer, you can take that into account by basically doing a small modification of this. But I think for the interest of time, I'll skip that and go to the stochastic optimization, since I think for this application it's much more interesting to look at that. Okay. You can look at these, I'll make them available on the website. And see, so there's this. Yeah, I prepared way too many slides, I'm really sorry about this. If anybody worries about vanishing or exploding gradients, anybody? Okay, we'll talk in person. Anybody else worries about this, then you can send me an email, because there's some nice literature on this, and there are very nice links to the dynamical systems as well. So if you are interested, yes?
Why is it important to learn how these algorithms function? Or how is it relevant to the area of machine learning? Do I need to develop an algorithm by myself, or is there any available optimizers that can do?
Yeah, so that's an excellent question actually. Maybe I should have answered that at my very first slide. Why should you stay? It's Friday afternoon. No, I'm not. Yeah, it's a good question. Yes. So, and the answer is that there's so many algorithms available, and there's one coming out every week. So, right, as a practitioner, you're like, oh yeah, which one should I choose? Should I choose the newest one, or should I just stay with what I have? So, for the purpose of keeping up with the literature, it's useful to know a little bit about the general concepts about what is known, what is not known, because some literature may be also a little bit misleading. They say we have exponential convergence. You're like, wow, that's super fast. But what they actually mean is linear convergence. But they call it exponential because it's something to the power k. Right, so they're knowing these concepts a little bit, you can be a little bit more informed about it.
Is it also relevant to the size of a problem that you are doing machine learning for? Or is it
yeah, so indeed, so what I'm going to talk about now, these stochastic methods, they specifically tackle the case where the computational cost is high because you have many samples. Some of these other methods you may want to take into account that your search space is high dimensional, so you have many parameters that you're looking for. And there, it's kind of easier to get a very ill-conditioned problem because there, there's lots of directions where something could go wrong. Yeah. So stochastic optimization. All right, there we go. So stochastic. I'll just stay here for a minute. Stochastic optimization. The idea is to step away from this idea we had earlier in just minimizing the cost over all the training samples, and say instead, well, what I want to do is minimize the expected loss. And in expectation over, let's say, my data generating process. So in expectation over all possible samples that I could possibly have. All cat pictures, right? Of future and past cats, for example. If I want to solve an expectation minimization problem like this, then stochastic gradient descent says that's no problem. All you need to do is iterate like this, so WK, that's the same I had before, there's a step size, and there's my gradient evaluated at one sample. So at every iteration I draw one sample from this data generating process, I plug it into my cost function, and then I take a step in that direction, and then I'm at the next iterate and I draw one other sample. And then there's some theory that I'll try to summarize that says something about convergence of such a setup, where I just one sample at a time take a gradient step and another sample. Yes?
Why do they call it stochastic gradient descent and not point-by-point gradient descent?
That's an excellent question. I don't know. So the paper is from the 1950s, so maybe it was a very popular term back then. So I don't know. But it does come. It's actually.
Stochastic is uncertain or.
Yeah, that's right. Yeah. So I guess the stochastic comes in like you draw one sample every time, you take an expectation. But it does come actually in different names again. So sometimes they're called incremental gradient methods, or yeah. All right. So and then one very popular thing in machine learning is to use a batch. You've probably heard the term batching before. And it basically says, well, instead of taking one sample at a time, we're just going to draw a couple. Use that. Take the average over those couple of samples and use that as a descent direction. And then here, there's many flavors again, right? You can take, if I take as a batch my whole training data set, then I'm back at the usual case that I had before. But then I can't say whether it converges to the expectation of this thing. But those are a couple of subtle points that I'll try to skip over. Right, you could take a small batch, you go mini batching, or all kinds of fancy terms that they use. You could say you can take 10 samples, and then take a step, 10 more samples, take a step. The way I'm going to look at this is to tie it to what we've learned about gradient descent, is to say, okay, whatever we do here, I am optimizing the objective over my training set. Okay, so I'm sure that's my choice now. I'm saying there's a fixed training set and I want to optimize the cost function over that fixed training set. I just want to do it faster, more efficient. Right? The idea being that one iteration here is much cheaper than one iteration with all the training data. So if I do that, then I can think of this or this, the sampled gradient, they call it the sampled gradient, is just the full gradient right here plus an error. And this error is induced by not computing all the terms, but only a couple. Right? So that's the viewpoint I'm going to take, and then we can state the following. Or under these following assumptions, then we can state some things. So the assumptions are that the gradient direction that I'm sampling at each iterate is correct on average. So that means in expectation that the error is 0. Basically means that the gradient is unbiased, the estimate is unbiased. Right? It's not going to point me in slightly the wrong direction all the time. On average, it's going to point me in exactly the right direction. And you can do that, for example, by choosing this index set of your batches uniformly at random from your training set. And if you redraw that at every iteration, then you're good. Right? Then you have an unbiased estimate.
So in terms of numbers, if you have 1,000 samples, you take a batch of 10 and then you need to do it 10 times or 100 times?
I'll show a couple of pictures later. But it's so in practice, it turns out that, let's say, if you have 1,000 samples, you take only 10 at a time.
Yeah.
In the same number of iterations, you can get a comparable answer. So instead of doing, let's say, 100 iterations with 1,000 samples versus same amount of, same amount of iterations.
Yeah.
With only a few samples, I can get a comparable answer. Yeah. So the idea really here is to speed up the computations, and I'll be a little bit more specific in a bit about this. And the other thing that we need is that the variance of this error is also bounded. Then what we get is this. So this is I'll just take you through this formula step by step. But this basic algorithm produces these iterates in expectation again, because now we're doing some random sampling. In expectation, at my k plus 1 iterate, the difference from optimality is bounded by this whole thing here. So what's this mess? So this is just a constant that depends on the mu. Oh, that should be a small l. Sorry about that. That should be a small l. Bounded by this constant times the previous distance to optimality plus this term. So now we can see what happens if we start iterating this. This is going to be powers of this constant, so that's going to be fine. But I'm also going to accumulate these terms. So as I iterate, this error that I make at every iteration, it can accumulate. So there I need to be careful, but there are some things I can do about this. For example, there's an alpha k squared here. So after k iterations, I have k of these terms, but I can choose the alpha k to be order 1 over k. So then it says k times 1 over k squared, so then in the end it's 1 over k. So then this contribution from this constant will decay. The other thing I can do is this sigma, this variance of the error. If I make a better approximation as I go along with the iterations, then this sigma will also shrink. So these are basically the two tools I have to keep this term at bay, to keep control over this term. This term it's fine, right? And this is just going to multiply my error as long as the alpha k is small enough. This is going to be smaller than 1. Then I'm all happy. So that brings me basically to the two basic flavors of gradient descent or stochastic methods that you see. Is either we have linear convergence to a point close to a minimizer. So that's where we leave these terms to accumulate and hope they don't get too big. Then in a linear rate, so very, very fast, let's say, I'm going to get to a point close to a minimizer, and then I'm going to jump around that minimum for a while until I decide to stop. Or I can do decreasing the step size, and then I get a sublinear convergence rate because my steps are getting smaller and smaller and smaller. But then eventually I will arrive at the minimizer.
Is that one related to the term learning rate?
Alpha is exactly the learning rate,
Oh,
yes. Yeah, exactly. So they call alpha the learning rate. So as I mentioned, there are a couple of things you can do. They call it variance reduction, so there's one more of these terms, but it's nothing more than decreasing that sigma term that they dispense. So there are pictures as 1,000 words. With a fixed step size, looking at the distance to optimality, so the CWK minus CW star goes like the blue one. So it goes down linearly, at one point it tapers off and then it starts wiggling around. So that's the noise that I keep adding to the system. I'm just going to jump around to minimum and not go anywhere. Then I can reduce the step size. So every step, my steps get smaller and smaller. And I keep on converging. It will go on for a while, but it goes slow. It goes a lot slower. Then the other thing, which maybe you think that's the silver bullet, right? It's going to work always, but I choose the example to exaggerate the differences a little bit. That's the variance reduction. So that means that every step I'm going to take a larger sample. But the trick there is you need to make the sample larger at exactly the right rate. If you make it large too quickly, then you're just doing a lot of work for nothing. If you make it large too small, then you're going to be stuck kind of wiggling around. And of course you don't know whether you are wiggling around. Okay, but if you do it exactly right, then you can get linear convergence all the way. So that's kind of the balance that you have to play, and practical methods kind of do something in between. Try to be clever. Like in the beginning I'm going to do this because it's very fast. At one point maybe I want to step over to this. If it doesn't work out, I can always fall back to the orange one because it's going to converge no matter what. Okay, so then the last thing I was quite excited about, leaving the stochastic optimization behind for now, is visualization. So we have these complicated loss functions in many, many dimensions. There's choices we can make on the network architecture or the regularization term or the kind of optimization method even we use to explore this parameter space. So in the end we want to draw a picture, right? We want to see what did we get? What does my landscape look like? Of course, even in more than 3 dimensions it will be very hard to visualize this landscape. But we also know that many of these problems, my iterates are not going to be, they're not a random walk, right? My iterates are not a random walk, they follow a certain path. And the path goes along the steepest directions first. So the idea is to keep track, if you want to visualize this, to keep track of all the iterates. So these should be W's again. You saw these are the last slides, so we're going to add that at the last moment. The D should be W's, those are the iterates. So I run this algorithm for n iterations, and then I look at the difference between my initial iterate and my final, the first iterate and the final, and then the pre-final and the final. So I make a big matrix out of all these iterates, and then what do I do if I have a big matrix? I want to know something about it. Right? I take the SVD or the principal components or whatever you want to call them. So I compute the two principal components, the two largest directions of this matrix M, and along these two directions I'm going to plot this landscape, this cost function. And then we get a picture like this. So this is a standard benchmark optimization problem in 10 dimensions, and here projected it down to 2 dimensions. I think this captures like 70% of the energy in the directions, and I can nicely plot what my objective looks like and how the path is going to the minimum. There's actually a nice paper that I'll point you to that kind of explores in this manner various network architectures and shows that some of them give rise to horrible landscapes that you would never want to optimize. And some of them give rise to really nice convex, hilly landscapes that you would be very comfortable in optimizing on. Alright, so the summary: supervised learning leads to interesting and structured optimization problems. So there was the sum, and there was the loss term, and there was the regularization term. We can kind of take into account the structure of all of these things. There are many specialized algorithms available to take advantage of all this structure. So in particular, the stochastic optimization was built to take into account the sum structure of the optimization problem. Right? I had a sum of many terms, so I can just say, well, I'm going to approximate the sum by sample average. And there are other tricks that you can do to take into account the structure. So if you think you have a structured optimization problem and you want to discuss it, then feel free to send me an email. And finally, the stochastic methods can be usefully analyzed as just gradient descent, where at each step you introduce an error into the gradient. Alright, so then further reading, so these slides will be available and you can